Okay, good afternoon, everybody. Thanks for coming. So it's our course called Computational Gas Dynamics for PhD students. So I think that everybody here are PhD students from School of Astronautics, right? Yeah, okay. So today our first lecture, and it will be just introduction. I'd like to explain what is the subject and what is the expected outline of our course, and maybe at the end of this class we can discuss the formalities and so on. So today I'd like to discuss with you and explain what is the computational gas dynamics. And the first topic will be Euler equations, because everything in this field is based on the Euler equations, and if we want to consider more complex flows, viscosity, Navier-Stokes equations, chemical reactions, whatever, everything is based on Euler equations. That is why we should start with this topic. So let me introduce myself. My name is Pavel Utkin. I'm professor at our School of Astronautics, and also I belong to the International Center of Applied Mechanics. And actually, I think it's important to explain a little bit about my background, because it can explain why is this topic of great importance. So the first small subsection of this lecture is about myself. So my alma mater is Moscow Institute of Physics and Technology. So I graduated from this university and obtained all my degrees, bachelor degree and master degree and PhD degree from there in 2006, 8, and 10. So this is the campus of this university. So it's a very good technical university in Russia. It's much smaller than HIT. It's small technical university. So HIT is like Moscow State University. It's a huge university, and this is a small one. And so in Russia, the activities about educational activities and research activities, they are separated. So it's for educational activities, and Russian Academy of Sciences is for research. So I worked at the Institute for Computer-Aided Design of the Russian Academy of Sciences. So it's just in the center of Moscow. And this is the building of the Hotel Beijing, so famous hotel in Russia, in Moscow. So I worked there at MIPT and Institute for Computer-Aided Design. And since 2023, I have been working as a professor here at HIT. So there are three main research topics. The first one is numerical simulation of compressible flows of chemically reactive media. So numerical simulation of propagation of shock and detonation waves in gaseous mixture. There are some practical, so the practical importance and relevance of this field is determined by works for promising rocket engines and also explosion safety issues. For example, if you have a coal mine and you should so prevent the damages, devastating explosions, so we should know how to simulate the propagation of shocks and detonations. Detonation is a supersonic combustion wave. And also, to know the mechanisms of these processes, we should study, first of all, some fundamental problems. So, for example, this problem is about how to initiate this supersonic combustion when shock wave reflects from profiled end wall of the channel. And depending on these different curvatures and configuration of this reflector, we can obtain different modes and try to find the geometry that provides the initiation for the lowest incident shockwave Mach number. So it's also important because I pronounce some words such as shockwave, Mach number. They're important for our course, and later I will explain in more detail what does it mean. So now it's just some pictures just for your understanding, but later I will explain in more detail what does it mean. So here we can see that shockwave, some disturbance, gas propagates from left to right, interacts with this wall, and this it's numerical simulation. So the upper part of this picture is visualization of density gradient magnitude. So it's like Schlieren visualization in experiments, and this is temperature field. So if we see blue color, so it corresponds to lower temperature, and red color to 4000 K. it means that this hydrogen mixture explodes and burns, so the temperature is very high. So this topic is also of interest from the point of view of hydrogen energy, because it's the most ecological and promising fuel, and in many aspects it's much better than hydrocarbon fuels. So this topic is also important from this point of view. So one field is the study of mechanisms of initiation and propagation of such detonation waves. So we simulated it using our own in-house solver. Today we also will discuss why do we need to write our own codes, and because there are a lot of existing software solvers. So this is also very important. What tools do we use? So our course is about not just to know how to do such simulations and prepare such videos and movies, but to understand what is the basics. So what is under all these simulations. Another topic of interest is so-called particle resolved simulations. So all media around us are not just one phase; they are multi-phase. For example, even in this room, so we have air and small particles of dust or something else, and so it's not possible to have just pure media. So all media are two-phase, and if the number of particles is large enough, once again, for example, like in coal mine, or if we speaking about some production, chemical production or food production connected with fine particles of organic dust or something like that. So we have two-phase media, and under some conditions it also can ignite, explode, and but if we want to know how it happens, we should be able to simulate this process with detailed resolution of each particle. So in this study we consider two, so microscopic particles. So this scale are in millimeters, and then a supersonic flow. So again, maybe a new word for you, supersonic. And in this flow, this flow pushes these particles and they move. And the goal of this study, the goal of this work was to explain the mechanisms of motion of two particles. They affect each other. So what is the mechanisms of influence, how one particle affects to another particle in the supersonic flow. We also compared it with experimental data, and finally got result and published a paper in the Shockwave journal with both numerical results and experimental results. So the third topic of interest is, for me, is numerical simulation of two-phase flows. So when you try to simulate this problem not with the detailed resolution of each particle, but considering the second phase, solid phase, as like also continuum media. But all these topics are advanced topics, and it's just for general impression for you. We're not going to discuss in detail all this complex physics and mechanics. Once again, we're interested in detailed understanding of what does it mean with this line, and what are the relationships to one and to another sides of the shock waves, and how does it come from equations. Okay, it was a little bit about myself. And so what is computational gas dynamics? What does it mean? Maybe you should know the term computational fluid dynamics or computational fluid mechanics. So we should discuss some maybe differences and specific features of gas, fluid, solid. So what does it mean? So during my lecture I will, so everything that I use, it's not just, I did not provide it by myself. So there are good books, and my goal is to provide you relevant references for you be able to to more and more detail all these topics. So almost each slide I will supplement with reference, and at the end of this lecture I will provide relevant references, and I suppose you to read these books, to take these books, Actually, this book, Anderson Fundamentals of Aerodynamics, is very popular in China. So in China, in many universities, they use this book, and this book is really great. Solids, liquids, and gases. So a distinction between solids, liquids, and gases can be made in a simplistic sense as follows. So put a solid object inside a larger closed container. So if you put something in containers, some solid object, the solid object will not change its shape, its boundaries will remain the same. So quite contrary, if you put a liquid inside the container, the liquid will change its shape to conform to that of the container and will take from the same boundaries of the container, right? And the gas inside the container completely fill completely fill the container, taken on the same boundaries as the container. So the word fluid is used to denote either liquid or gas. So from point of view, so there is a solid and fluid. In comparison with solid in this sense, so fluid and gas actually are the same. The more technical distinction is in shear stresses. When a force is applied tangentially to the surface of the solid will experience a finite deformation. And the tangential force per unit area, the shear stress, will usually be proportional to the amount of deformation. So that's a solid body. So I know that some of you is solid mechanic guy, some are fluid mechanic guy, and so it's useful to understand the differences. In contrast, when a tangential shear stress is applied to the surface of a fluid, or liquid, or gas, so it will experience a continuously increasing deformation. And shear stress usually will be proportional to the rate of change of deformation, not the deformation, but rate of change of deformation. So in fluids or gases, we do not have the same shear stresses like in solid body. And in this sense, so we can use fluid for both liquid and gas, doesn't matter. But in fact, for sure, liquid is not same as gas because of densities, and because of that liquid under normal conditions is incompressible media, and gas is compressible medium. However, under some conditions, the compressibility of gas is not so important. So this compressibility becomes more and more important for high speed, high pressure applications. So fluid mechanics concerns the different motion of fluids, and computational gas dynamics is a part of a broader field of computational fluid dynamics. So CFD stands for computational fluid dynamics, while gas dynamics is just a part. It's almost impossible to cover all different motions of fluid on gases within one course, because they're very, very, very different. So here I provided just a number of two snapshots that illustrate different types of motion of fluid or gas. So I enjoy this Van Dyke album of fluid motions, famous book. It's composed of different snapshots illustrating. It provides the most impressive and clear illustrations of different types of instabilities, of motions of liquids and gases, and I recommend you to see it. Traditionally, the rough classification of flow types are the following. So gas dynamics is also referred to compressible frictionless flows. And so this is a topic of interest for us. Viscous flows, boundary layers, and turbulence. For sure, boundary layers and turbulence, they also could be compressible. But, within the scope for educational purposes, usually different theories for boundary layers and turbulence, they're usually illustrated for incompressible frictional flows, And there are also types of flows that can be considered theoretical using different analytics, so such as potential flows, rotational frictional flows. For boundary layers and turbulence, so this is the famous Kármán vortex street. So this picture illustrates vortex street behind a circular cylinder at Reynolds number 140. So it's for water. Water is flowing at 1.4 centimeters per second past a cylinder of diameter 1 centimeter. And in this case, you will get some beautiful vortices in the wake behind this cylinder. And this is quite contrary example of compressible flow. So it's a supersonic fly of a brass bullet, experiments of Ernst Mach. We will discuss it in more detail later. So this is the first picture in the world of a shock wave. Shock wave that moves with a supersonic velocity. We will be interested mainly in high-speed flows of inviscid perfect gases and flows with shock waves within our course. So we will not discuss this part. We will discuss this part mainly. Although there are the models, the equations that we will discuss, and numerical methods that we will discuss, they also can be used to study some turbulent effects, but this part is main for us. So I've told you about compressible flows and incompressible flows. Once again, we should clearly make a distinction between them. So a flow in which the density is constant is called, obviously, incompressible. In contrast, a flow where the density is variable is called compressible. In fact, all flows, to a greater or lesser extent, they are compressible. So truly incompressible flow where the density is precisely constant does not occur in nature. However, there are a number of aerodynamic problems. So I also teach course on aerodynamics. So that is why some examples from the field of aerodynamics are close to me. It's so possible to provide some examples from other fields, but we belong to School of Astronautics, so it's also close to all of us. At least it should be close to all of us. For example, a number of aerodynamic problems, they can be modeled as being incompressible without any problems. For example, the flows of homogeneous liquids. So they are treated as incompressible under normal conditions. Although for high pressure applications, for sure, we should take into account the compressibility of even water. But under normal conditions, so the water is incompressible. The flow of gases at low Mach number. So again, Mach number. So if Mach number of the flow of gases is low, actually we can consider it as incompressible. If Mach number is less than 0.3. So if Mach number is less than 0.3, it's always safe to assume density is constant. Actually, this was the flight regime for all airplanes from the Wright brothers' first flight in 1903, just prior to the Second World War. But nowadays, so if we want to move into high-speed flows and real planes, the media must be treated as compressible. For such flows, rho can vary over wide ranges, wide latitudes. So again, incompressible, viscous, inviscous, high speed, low speed. So it's not possible to cover all these regimes. So now I just want to illustrate you that the wide range of parameters. And for example, if 50 years ago it's possible to be a researcher or a scientist who is an expert in all types of flows and so on, nowadays people have usually very narrow specialization. So if you understand the mechanics of compressible flows, so it's one thing. And people who simulate or understand the mechanics of incompressible flow, so they're another people. And it's not usual today that for somebody is an expert in all types of flows, and because in each field, in each direction, so greater number of results have been obtained, and so it's not possible to know everything from this area. I told this Mach number. So this is just a reminder. So what is Mach number? Maybe you know, maybe not. So Mach number is a very important dimensionless parameter. So dimensionless parameters or criteria, so they're very important from theoretical understanding for theoretical consideration of all these topics of continuum medium mechanics. So Mach number is the ratio of local flow velocity, or usually the absolute value of local flow velocity, to speed of sound. So another very important concept of speed of sound. So the flow can be subsonic if the Mach number is less than 1. Transonic if in the flow you have regions where locally Mach number is greater than 1 and somewhere it's less than 1. And supersonic if everywhere, almost everywhere, the Mach number is greater than 1. And even in this case, the behavior of media, in all these cases, so this behavior is different. And even if we consider compressible flow, in-viscid flow, but for different types of flows, we should apply sometimes different numerical methods. So even for this specific case, but for different Mach numbers, we should apply different numerical methods to get better results. So that's why, and that is one of the reasons we still discuss these topics and issues, because it's almost impossible to find, to create, to provide the best solver, the best software for all the problems. What is speed of sound? So during our course, we will get the exact definition, and we get it from defining system of equations, and that's very important. But it's possible also to get some physical explanation. So speed of sound. So sound is the waves. So I'm speaking and you can hear me because of propagation of sound waves. From the point of view of compressible media, sound wave is a shock wave with very, very low amplitude. So it's that goes to 0. So it's very weak shock wave. And however, although the amplitude of the shock wave is very small, it propagates with a certain velocity in the media. And that is a specific feature of hyperbolic system of equations, because the equations of Euler equations, gas dynamic equations, they're hyperbolic. And the existence of these very low intensity waves that propagates with a finite velocity is a specific feature of the hyperbolic model. It is known maybe from courses on general physics, maybe you should know, that speed of sound can be computed as dp over d rho under constant entropy. This is a general expression. For the ideal gas, it can be simplified to this well-known formula. How to do that? Because for the constant entropy means that we should compute it for the isentropic process. For isentropic process, p over rho to the power gamma equals to some constant. Then we can express pressure as a function of density and take the, it's misprint, should be dp over the rho, and take the derivative. Then it will be constant multiplied by gamma rho to the power gamma minus 1 as the derivative of power function. And then we express this constant from here and set it here, and then we easily get this formula. Square root from gamma p over rho. So it's the formula for speed of sound in ideal gas that you can find in any book. What is gamma? Gamma is Cp over Cv, where C is specific heat capacity under constant pressure, this under constant velocity. So the thing is that for compressible media, we should also take into account the thermodynamics. The thermodynamics of media means that we should know all these specific heat capacities, specific heat ratio. We should solve energy equation because we have compressibility. That's also the difference between compressible and incompressible considerations, because for incompressible media, actually, if density is constant, we do not need to use equation for energy. So everything is different. Even the structure of the equations, the number of the equations, everything. Mach number. Mach. So this criteria is named after Ernst Mach. He was an Austrian physicist and philosopher who contributed to the understanding of the physics of shock waves. So actually the world knows him because of his contribution to the field of shock waves. Once again, so what does it mean? It's the ratio of the speed of flow of object to that of sound is named the Mach number. So here it states that the ratio of the speed of flow or object. Yes, the previous definition was the Mach number is the ratio of the velocity of media to the speed of sound. Maybe you can know him from your lessons on philosophy if you had it. So as a philosopher of science, he was a major influence on logical positivism and American pragmatism. Actually, he criticized Isaac Newton's theories and actually foreshadowed Albert Einstein's theory of relativity. So he's very famous. And it was he, so that for the first time he obtained these snapshots of the shock wave. So it was in 1884, Ernst Mach's experiments on the registration of shock waves. But to do that, prior to that, first of all, people they invented the high-speed photography. So first of all, they invented the registration technique, how to do that, and after that, it became possible to get some snapshots. Actually, these are experimental pictures. You can see these waves, and I have shown to you previously this movie, and this movie. So this type of visualization in numerical simulation, people use this type of visualization to mimic, to reflect this experimental method for registration of shock waves. So this technology, so what is it? Why do we see this line in experiments? Because it's a special technology. It provides visualization of strong gradients of density. So for example, if density of media, of air, is almost constant here, we can see just black color. Or here, so it's low, it's high, but nevertheless, if it's almost uniform, we do not see anything. But if somewhere the density changes very strong, in a sharp manner, then this Topper technique, it provides this very sharp, very visible line. And in the same manner in simulations, if we compute some problem with the shock waves, then compute the field of density, then they compute the magnitude of gradient of density, we will see the result that so when we cross the shock wave, we will get this line. So the first benefit which the physical sciences reaped from high-speed photography was the visualization of shock waves. So once again, first of all, high-speed photography. Adopting the Schlieren technique from Topper, Ernst Mach photographed and measured supersonic waves in the wake of rapidly moving projectiles, as well as sound waves generated by sparks and jets of compressed air. Actually, he saw that for subsonic muzzle velocity of a bullet, so if the speed of this bullet is not so high, actually, what does it mean not so high? So it's less than speed of sound, then no shock waves. So for slow moving bullet, you will not see this picture. However, if the speed is high enough, higher than speed of sound, then you will get this shock wave. So it should become visible only above the speed of sound 343 meters per second. In dry air at room temperature proved correct. So only if the speed of this object is higher than approximately speed of sound in air, then you will get these shock waves. Yeah. So I'll try to explain to you, so what does it mean, CFD, right? Computational fluid dynamics. And I try to explain to you the differences between, fluid and gas and liquid, that in comparison with solid, the liquid and gas is the same, but there are differences between liquids and gases, especially taking into account the different possible regimes of motion. On internet, you can see, you can also find these funny abbreviations for CFD, but actually they all reflects the real challenges and specific features of this process. So, for example, what does it mean, CFD? Colorful fluid dynamics, so it's a very popular definition. I have already shown to you these, beautiful movies and so on. So, on one hand, yes, so the one of the outcomes of such CFD simulations is these beautiful movies, and that's great because sometimes it's also it's necessary to show to students and somehow maybe they will be interested in these topics to see some if they see some movies. But on the other hand, sometimes people use too much, these movies and so on, because they try to shade the lack of understanding of the processes using these movies or pictures. So sometimes maybe it's more useful and important to plot just general graphs to use these animations. Computers for designers or directors. If you have some grant or a contract, it's very pleasant and good point if you're able to, on your final presentation, provide such movies, and it looks like you worked hard on this project because you do such simulations and you can provide these beautiful movies. Completely false data. You can understand that actually using your computer model, you can compute whatever you like. And if you're not careful enough with the models, with the numerical methods, if you're not an expert and you just take ready software and use it like a black box, you can obtain totally wrong results. And that's a big problem. That is why CFD for somebody is completely false data. Costly financial drain. CFD simulations is a source of huge computational costs. For example, if you need to compute 3D non-stationary problem, for example, a flow around a rocket or a plane, and so you need to solve 3D problems, and you need supercomputers for that, and everything you should pay for that, for time or on supercomputers, and sometimes maybe it was not necessary to do that, but anyway, so costly financial drain. Confusing flow diagrams, so it means that even for the movies I have shown to you, the shock wave structures can be very complex, and if you do not know what does it mean, it's very complex for you, so they're just confusing flow diagrams. Or computations for decoration, so it's again about computers for designers and directors. So it mimics that nowadays CFD is, from philosophical point of view, before computers, there were two main ways how can we study the nature. So analytics and experiments. So there were two main branches, types of knowledge. But after that, we have CFD, we have simulations, and it's something like in between. So for sure, I consider it like a theory. So for me, theoretical consideration is just the same. Analytical or computational doesn't matter. Everything is theoretical. But actually, many people consider it like the third way of exploration of reality of our nature. So CFD is not just analytics, and it's not experimental data. It's something in between. And they try to speculate on these topics. My point of view, so my opinion is that actually we should know the structure of equations, we should know the solutions of equations, we should know the properties of numerical methods, and we should accurately solve the equations we have. And in this sense, actually, this I will show to you later that for sure it's a sort of art, not just very. So there are few very strict results like an algebra or something like that. In many aspects, it's like an art. But where it's possible, we should keep the mathematical strictness of the science. Maybe for some people, if it's not obvious for you, anyway, I prepared the slide that I show for students. Why do we need CFD? Especially it's important for the experimentalists, because some people think that, okay, so why do we need simulations if we can just if we have experiments and we can take all from these experiments. Actually, in some cases, a full-scale experiment is impossible. So this is the snapshot picture from this paper about simulation of supernova explosion. So in some astronomy applications, it's not possible so we're not able to say to a star, okay, just explode and we will measure something. No, it's impossible. We should do simulations for that. In many cases, a full-scale experiment is not able to give exhaustive information about the process. So the problem is that actually all processes in our life are three-dimensional. And so if the process is three-dimensional, your experimental techniques are usually provide you only just some 2D slice or just measurement in point or another point. So it's not possible to get the full picture of the 3D process from experiment. In simulations, you can measure everything in each point. You can provide either surfaces, slices, whatever you like, or provide either surfaces covered with different values. If you did realize and understand what does it mean, it can provide you very helpful, fruitful information for about the process. For example, this is the closer to our thing. So this is a movie of operation of rotating detonation engine. So this is a very promising type of engines that is studied in China and all over the world. Promising rocket engine, where the fuel is burned in a supersonic detonation wave that propagates in coaxial gap between two cylinders. So this is an example of the real 3D process. So how can we, it's really difficult to, it's impossible to see these pictures in experiments. So in experiments, you can just have a number of videos from this side or from this side, and that's it. Only simulations can provide you the understanding of the mechanics of propagation of burning wave in such complex system. But the problem is that people try to use it in reality because it can provide the high efficiencies for rocket engines, and there are a number of existing devices. Often experiments are very expensive. So the last here, it's very, simulations are cheap. For sure, it's not difficult. That's not easy. It's a difficult problem to create solver, to adjust parameters and so on. But once you have already done it, you can just run your simulations. And although for time of supercomputer you should buy it, it's also not cheap. But actually, it's cheaper than do real experiments. And also there are also safety issues in the field of explosions, for example. So I'm about compressible flows, high-speed flows. Experiments in this area are usually dangerous, and so you are not able to do them in this room. For example, you should have special apparatus, and so special building, maybe not in the center of the city, and so on. So many difficulties about the full-scale experiments, in contrast to simulations. That is why we really need simulations. What time should we have a break? At 35 minutes or 25 minutes? 35. 35. Okay, 35. Again, the slide that I try to show students for they to be engaged in this subject. We're interested in CFD and aerospace research. So this is a rocket simulator that is just next to this building. Consider this one specific, device of rocket industry, Korea rocket, Chang'e number 5. Even here we can see a number of problems that can be solved, that should be solved, that were solved using methods of computational gas dynamics. For example, external aerodynamics, the shape of this part of this rocket. Aerodynamics shapes optimization, thermal protection coating. So how can we compute the heat fluxes to the surface? Because according to this data, we should give suggestions about the material of the coating of the rocket. Or internal aerodynamics. So we have engine, and for this rocket, there's two-phase flow in this engine. It's not just gas dynamics. We have liquid and products of combustion product, and actually external dynamics and internal aerodynamics. Although we solve almost the same equations, computational domain is totally different. And the methods and statements of the problem and the numerical approaches to external dynamics, they are not the same as for internal dynamics, and we should know that. Or some related problems. For example, the interaction of burnt gases with the launching platform. So these burnt gases, they interact with platform, and we should know the safe distance around this rocket, and so pressure loads on different parts and so on. So many different problems that can be solved, and so we should have, once again, different tools for the solution of these problems. Typical stages of CFD simulation. So although the simulations they're all different, it's possible to provide some typical scheme. How should we solve this typical CFD program? Usually everything starts with building the geometry of the object under consideration, or geometrical modeling using some CAD system, for example. For sure, we can do it without CAD system, but if you're talking about some real objects such as engine or I don't know, wing of a plane or something like that, you should have the real geometry of this object. Engineers or constructors, they provide the real geometry of this object as a CAD model, for example, in SolidWorks or another system. We should take it and build a computational grid around or inside this object, depending on the problem under consideration. Computational grid, first of all, geometry and then computational grid generation. So there are many types of computational meshes, once again, depending on the problem under consideration. I can just maybe skip these points and then go back. I enjoy this slide very much, computational grid. So suppose we have a problem, we should compute flow around this cylinder. But depending on the problem under consideration, for example, maybe we need to know the flow in the core of the flow. Or maybe we need to know the parameters on the surface of our cylinder. Or maybe we need to know parameters of the shock wave that propagates around the cylinder. So depending on the problem under consideration, we can propose different numerical grids. So it's also part of numerical algorithm, and it's not possible to say, okay, I have the best numerical grid generation. So grid generation, different types of meshes are possible with, quadrilateral cells or triangular cells with the resolution boundary layer and so on and so forth. I also like this. So there are a number of good books in Russian in this field. Unfortunately, I am able to read in Russian. That is why sometimes I will provide you some citations from that books. So Godunov is one of the most famous Russian scientists in this field. He proposed his Godunov scheme, and now Godunov type schemes are finite volume schemes. So they are standard they are widely used in all types of software for simulations. And in that time and now, the problem it's always an ad hoc procedure to provide this numerical mesh. And that is why I told to you that it's a sort of art. So it's not possible to say that CFD is just science like pure mathematics, because depending on your problem, depending on the flow type, you should provide different solutions in building your numerical algorithm, computational mesh, and so on. Even for such a simple problem. But even here you can find totally different types, for example, of computational mesh. Not saying about that, depending on the computational mesh, you should use different numerical methods, because one method can deal with these triangular cells, another method can deal only with these rectangular cells, and so on. And for example, if you're able to use this simple mesh, actually that's okay, because the accuracy of the method is highest here and lowest here. So although the triangulars can be used for approximation of complex geometries, the algorithm will be not so accurate. In comparison with the case, we can use just square cells. So many different aspects. So okay, for example, you was given by geometry by somebody, and you put it in some CAD system. So you have digital representation of your object. Then you build some computational grid that is suitable for you. Actually, all stages, they're interconnected between each other. It's difficult to actually totally separate one from another. But anyway, the next stage is you should choose mathematical model. So what do I mean? So mathematical model is a set of governing equations. So there are a lot of different mathematical models, but we are talking about nonlinear partial differential equations. Euler equations or Navier-Stokes equations. So it's a mathematical model. So Euler or multiphase or something like that. After that, so okay, I'm going to solve these equations. Actually, you should specify also boundary conditions and initial conditions. They are also essential part of your mathematical statement of the problem. And once again, about the pure mathematics, the problem is that everything that could be obtained analytically for these equations have already been obtained almost. That is why we need simulations, because for almost all problems of interest, we are not able to provide some analytical solution. That is why, okay, we specified our system of equations, boundary conditions, initial conditions. Then we should provide some numerical method that will be used for the solution of this system of equation. During our course, we will talk about finite volume methods and Riemann solvers for Euler equations. I will explain to you what does it mean, finite volume method, Riemann solver, and so on and so forth. And it's also important to mention that on each stage of this process, you provide some mistakes in your final result. For example, you need to simulate some flow in some device. But it's almost impossible to take into account all different, features of the geometry. So you just cut them. So you made some mistakes. You define some mathematical model. For example, you say, okay, I will not take into account viscosity of gas. And again, you made some errors and mistakes. Then you say, okay, I will choose second order numerical scheme. And at this stage, you provide some error of numerical discretization. After that, you use some software or you write your own in-house solver, and you have also errors regarding your, that you use your computer. Errors of round of errors because of your simulations. And ultimately, you get some result, and for sure, it differs from nature, because you have a lot of different errors. And for sure, it's your goal to understand, and you should be able to answer the question: what is the effect of all these errors on the result? And maybe your result is totally irrelevant because of all these errors. So this is also very important. Simulations. So okay, you have chosen your numerical methods and software. You do simulations, maybe using high-performance computing, and then you analyze your simulation. And if something goes wrong, you should, go back to one stage or another stage. You should refine your mesh, or change maybe statement of your problem, and so on. So this is a typical flow chart of actually any simulation. And this is just example. For example, we need to compute the flow or heat fluxes on this surface. It's a supersonic flow around the triangular ring. So that was current in ANSYS fluid. For supersonic flow, we know, again, from theoretical consideration, we should know the correct inlet boundary conditions, outlet boundary conditions. So we should specify that we will solve our problem in this domain. Then we should build the numerical grid. For example, if we are interested in heat fluxes on the surface, we should use the refined mesh near the surface of this body. If you really need these viscous effects, then we say, okay, that we will use Navier-Stokes equations and some turbulence model for that. Then we run simulation. In case of ANSYS fluid, maybe we even do not know the exact details of the numerical method. We have just number of buttons how to choose one or another solver, and then we get a result. So this is supersonic flow around this wing. Again, shock wave, standing shock wave, the Mach number, field of Mach numbers, the pressure field, and during our course, we will discuss the main stages of these simulations of real-world processes with a focus on numerical methods. So it's not possible to discuss with all the stages with the same extent of detailization. We are going to discuss how to build computational mesh. It's not the question of interest for me. We will not discuss how to derive mathematical model. For us, Euler equation will be just an axiom. So we will say, okay, we know that, for example, we believe that Euler equations are correct. And so our goal is to understand the properties of these equations and how to build the most accurate, robust numerical methods for the solution of these equations. And the idea is that the best numerical methods should take into account the properties of the solutions of the system that you solve. On this way, you are able to provide the maybe not the best result, but the most physically relevant result, I believe so. And we will not discuss how to build these pictures, although it's also very important, and you should learn how to do that if you are going to be a researcher, to be a scientist. We will focus on the construction of the numerical methods that take into account the properties of the system of equations. So the second part of the lecture will be about Euler equations. Yeah, okay, just the last slide about the introduction. Why do we need CFD? And what is computational gas dynamics? So why do we still need to develop our own solvers? So we have OpenFOAM, we have Fluent, we have ANSYS, we have COMSOL, and many other tools. So there are a huge number of developed commercial software and open source solvers, and in-house solvers also. Also, people, researchers, they write their own in-house solvers, and very often they're available for downloading. There is no universal best solver because of a variety of possible types of flows. So we have discussed just now. Subsonic, supersonic, laminar, turbulent. For incompressible flows, we don't have speed of sound. We have speed of sound for compressible flows, and so on. In each case, you may need to apply another numerical method. There is also issue from mathematics. The result of solving of a nonlinear system of partial differential equations, generally speaking, is not separable from the numerical method of computational algorithm. So for sure, for linear problems, we expect that the classical concepts of accuracy, stability, convergence, they are valid. But for nonlinear problems with the shock waves, the descriptions, the definitions of stability, they are much more difficult, and you may obtain unexpected results. So if you solve real nonlinear problem, and if the problem itself is not stable enough, you can see that the result depends on actual numerical method in use, at least in some extent. That is why you should understand the properties of or for example, in this problem with moving bodies again. So the result will depend on assumptions that we use to compute the motion of this body, interaction of the fluid or gas with the body. And finally, if you do want to do fundamental research using simulations, sooner or later you will have to get your own tools because so Fluent, CFX, they're okay for engineering simulations, right? But if you try to explore to know some new effect, sometimes that's not so good, because if you have an experience in CFD in simulations using, for example, Fluent or CFX. Sometimes you just impose some boundary condition or some option of the solver, and you do not understand what does it mean, and that's very bad for your fundamental research. That is why, anyway, now in 10 years or in 50 years, I believe that so people will develop their own solvers anyway. Okay, so the second part of our first lecture is Euler equations. So this is this course is officially English taught course. That is why I do not provide some Chinese on the slides, but for bachelor students, for the course of aerodynamics, I try to add more Chinese because I understand that it may be important. Is it correct? Oh, yeah, Euler equations. Okay. The governing equations of gas dynamics are expressions of conservation of mass, momentum, and energy. And as I told to you, I consider them in this course just an axioms. So we do not try to get mass, momentum, and energy equations from some first principles. No, we just say that they are valid. So we believe that the Euler equations are correct. And conservation, conservation requires that fundamental quantities are neither created nor destroyed, but are only redistributed or except in mass, converting from one form to another form. For example, if momentum increases in one place, either momentum or equivalent amount of energy must decrease someplace else. That's it. Conservation of momentum and energy is extremely complicated for a general physical system. Yeah, so it's sometimes you have additional factors such as combustion or gravity or electromagnetic force or chemical reactions, viscosity, we do not consider it. So we try to build the simplest possible model, not the simplest possible model, but just Euler equations without additional forces and factors, and understand the properties of the solutions of the system. To keep things simpler, traditional gas dynamics concerns inviscid flows of perfect gases. Yeah, also the equation of state of the medium can be also very complicated. We consider they are just perfect gas, originally free of forces except for pressure. Yes, which eliminates all influences on momentum and energy except for redistribution and pressure. So just classical Euler equations. We start with integral form of Euler equations. During this course, I will show you different types of form of notations of Euler equations, and they are important because different numerical methods, so different theoretical results are simpler to obtain using different types of notation of Euler equations, and numerical methods are also written starting with different form of Euler equation. Integral form is the basic one because Euler equations, they admit discontinuous solutions. And that is why we should start with a form of notation that also admits integral solutions. That is why we start with integral form. Conservation, for example, we start with mass conservation law. Conservation of mass states that the total mass of universe is constant. In other words, mass is neither created nor destroyed, but can only be moved from one place to another. Then if mass increases in one place, it must decrease someplace else. So we consider this x-axis and in 1D. Yes, so another important feature, generally speaking, we should write 3D equations, but it's a bit difficult. Actually, you should understand that although now you can think that it's very simple things, and in fact it's not. And the solution of Euler equations is very complex and difficult. And that is why, for example, next lecture will be about just scalar conservation law, so a simplified model. So generally speaking, the numerical solution of Euler equation is very difficult. That is why people try to study simplified models and try to explain some concept using simplified models. And about 1D or 3D, for sure, we will discuss only one-dimensional problems. Although I plan to explain to you 3D finite volume method on one of the lectures, but on most lectures we will use just and discuss only one-dimensional equations. So this is x-axis, and we have this segment AB. So this is our domain in which we would like to solve our equations. I'll just illustrate the mass conservation law. T1 and T2, just two arbitrarily time instants. So this is a control volume in this xt space. And mass conservation law states that, so the integral from rho dx for T1 is the mass of gas in the region AB at T1. So the integral at T2 is mass of gas in the region at T2. And the changing of this value is due to flux through the boundary B minus flux through the boundary A. That's it. So the changing of mass in this domain is due to only fluxes through the boundaries of this segment from A to B. So here rho is density, u is gas velocity projection to the x actually. So u is not a vector. See here, u is a projection of velocity. Rho u is gas mass flow. Okay. Just in the same manner, we can write the momentum conservation equation and energy conservation equation. You can see that they are not useful. They are not convenient for understanding, so they're big enough, and that is why later I will provide you with much more convenient notation of Euler equations. But the primary are integral laws. So this is momentum conservation law, and actually it was this equation in differential form that was written by Euler in 18th century. Here we have also pressure work, and the energy conservation law. Here we have total energy per unit of mass. So in the same manner, the changing of total energy in this volume is due to fluxes of energy and pressure work. I do not pay much attention to the explanation. What does it mean, pressure work? So I suppose that your PhD students, that you have had some courses on continuum media mechanics or maybe fluid mechanics, you should understand what does it mean, pressure force. So once again, I consider that these equations are known. The problem here is that, so this is the total energy of gas. So this is the kinetic term, and this is the internal energy per unit of mass. So this is internal energy term. The problem that let's compute a number of equations on unknown. So we have mass conservation law, momentum conservation law, and energy conservation law. We have three equations, and unknowns are density, velocity, pressure, and energy. That is why we added equation for energy, but here we have internal energy. We should provide expression for internal energy, and this should be the equation of state. That's provide a relationship between internal energy and pressure and density of media. So this is the simplest possible ideal gas equation of state. And in this manner, we have the full system of Euler equations. Actually, if we put this epsilon to here and this energy to here, we have three equations and three unknowns: mass, momentum, and energy. And unknowns are density, velocity, and pressure. So that's it. Three equations, three unknowns. And we want to solve this, we know how to solve this system of equations in some specified domain with some specified boundary conditions. So these are Euler equations for compressible media. So rho is not constant here, and we do not take into account viscosity. So the inviscid motion of our gas. But it's not enough. So if you will solve just these three equations for these three unknowns without taking into account second law of thermodynamics, we can get wrong results, because from physics, from general physics, you may know that so all the processes that follow the second law of thermodynamics are possible. In addition to conservation laws, any physical system must also satisfy to second law of thermodynamics, which is stated in terms of entropy, S, or the specific entropy. So it's a sort of philosophical concept. There are many ways to define entropy, but it's possible to compute and to get the expression for ideal gas, the expression for entropy. You can check the other books from continuum media mechanics. That so the second law of thermodynamics states that the entropy of the system does not decrease in time. It should be either constant or increase. That is why the second law of thermodynamics is written in the form of inequality. That the system so this is the second law of thermodynamics. Why is it so important? Because it is known that even taking into account the second law of thermodynamics, so usually second law of thermodynamics it choose the correct solution. So the Euler equations can contain wrong solutions, unphysical solutions. And second law of thermodynamics, I will show to you how to what does it mean when we will discuss the shock waves. But second law of thermodynamics provides you to get the physically relevant solution and to cancel wrong solutions. But even in this case, Euler equations, they may not have a unique solution. So interestingly, but even if we take into account the second law of thermodynamics, what are the difficulties? So for example, the Euler equations, they may not have a unique solution. This is usually valid for stationary flows in the presence of discontinuities. A well-known example is the interaction of a stationary supersonic flow with a wedge. The so-called strong and weak solutions with an oblique shock are possible. So what does it mean? Let's add some mechanics. So consider, for example, this problem. So this is a wedge, and theta is the inclination angle, and we have a supersonic flow here. And mechanics says that if theta is not high enough, is not large enough, you will get this attached shock wave. And the flow changed abruptly across the shock wave. And it is known from theoretical, so it's possible to solve this problem theoretically. It's possible to find this beta angle for this oblique shock wave. From theoretical point of view, it's known that there are two possible solutions. So the shock wave may be here, weak solution, or here, strong solution. Weak shock wave or strong shock wave. And in reality, the same. So the weak solution is the most common solution, but sometimes you can get this strong solution. So even here, for stationary problem, with take into account second law of thermodynamics, you can get two actually solutions. How can we? So this is the analytical solution. So for example, we take some theta value, and for this theta value, there is 1 point corresponding to smaller beta value and greater beta value. So weak solution, weak shock, and strong shock. For any given upstream Mach number, so upstream, so it's the Mach number of the incoming flow, there is a maximum deflection angle theta max. So if physical geometry is such that theta is greater than theta max, so inclination angle is too big, then there is no straight, so no solution exists for a straight oblique shock wave. Instead, we will get the detached shock wave. Actually, I don't think that. So it's a topic for the discussion, for example, on the aerodynamic course. Maybe it's not too important for you. Here, I'd like to illustrate. So I use this example as an illustration for. Let's not so. You may not just just take some software, run it, and that's it, and get some result. So the problem is that even from mathematical point of view, you can have not unique solution, and you should understand what did you get. For any given theta less than theta max, there are two straight oblique shock solutions for a given upstream Mach number. Once again, so this is a very good example. It's possible to obtain the solutions but it's not maybe too interesting. We will discuss later the expressions, and that's important for the normal shock wave. For the normal shock wave, it's very important. Okay. Okay. This is also example. What happens if we do not take into account the second law of thermodynamics? So our course is about the finite volume schemes, and so I will explain how to get these formulas. So this is a general 1D finite volume method. So U is a conservative variable selector, F is numerical flux, and all methods, they depend on how can we compute this numerical flux. And it is known, for example, this rho numerical flux named after famous researcher Rho. And the thing is that original version of this numerical flux, it does not, so it admits the expansion shocks in simulation. So the second law of thermodynamics is not valid in this scheme. And in this case, your numerical solution will be wrong if you do not take into account these effects. So this is the solution of so-called Riemann problem. So Riemann problem is the problem when you, for example, at x equals to 0.5, initially have some parameters to the left and some parameters to the right of this continuity. And then after some time, you need to get some solution. And this solution contains a shock wave, a contact discontinuity, or a refraction wave. Once again, we will discuss all these things in more detail later. Just here, just an example. And here, instead of this continuous solution, and the expansion wave is a continuous solution, I have this actually shock, expansion shock, and this solution is not admitted. It's wrong solution. It's unphysical solution. It's just an example of what can you get in your simulations if you use the not appropriate numerical method. But now you can imagine, for example, this is 1D simulation, you know the exact solution, that's okay. But what if you apply this numerical scheme for a multidimensional problem and you don't know the solution and you get some effect? And you may consider this like a physical effect, and you can make a mistake. That is why it's very important to use physically relevant numerical methods. I told to you that so the integral form of Euler equations is not too convenient. So it's very physical. It contains everything that it should contain, including discontinuous solution, but they are not very suitable for the numerical solution. The most so if you open almost any paper regarding the Euler equations, compressible flow equations, you will for sure will see the conservation form of the Euler equation. What does it mean? So historically, so conservation form. It includes the so it means that it's differential equations. So the differential form. Historical differential equations are preferred to integral equations if for the reason that the differential equations are more compact. The differential form of the Euler equations is also known as the conservation form of the Euler equations. So how can we do that? So if rho, for example, on the example of mass conservation law, so if rho is differentiable in time, then you can provide this relationship between change of density in time with the derivative for density. Then, in the same manner, we believe that so rho u is differentiable in space, and then you can provide this relationship between these fluxes through the boundaries of our segment with the derivative of rho u. And then we have our integral law, okay, mass conservation law, and we put this expression here and this here, and then we get this expression. From a to b, the integral from a to b, integral from arbitrary time instance t1, t2, d rho over dt plus d rho u over dx equals to 0. Because t1 and t2 just arbitrary time instance, it means that this expression in brackets should equals to 0. This integral is 0 for any a, b, t1, and t2. That implies that the integrand is 0. Differential forms of conservation of momentum, energy, and the second law of thermodynamics are obtained similarly. The results are summarized as follows. So if you take any paper on this topic, you will see these three equations: 1, 2, 3. Usually people do not write the last equation, so they imply it. They all qualified researchers, they know that second law of thermodynamics should be, but actually it's not written usually. Mass, momentum, and energy equation. These are conservation form of Euler equations. And once again, when people write it, they understand that they can contain discontinuous solutions, but just for simplicity, we understand that we should solve integral form of Euler equations, but we just write this one. Mass, momentum, and energy equations. And so our course will be about this system of equations. How to solve them, how to build a numerical method for them, what the solutions can be here: shock waves, contact discontinuities, expansion waves, Riemann problem, and so on and so forth. I think that some practical part is also important. If somebody of you would like or have, I have some solvers, some programs for teaching tasks, and maybe I can ask you to run it and to maybe modify it somehow. But I plan to couple of lectures, couple of our classes. I will spend just like so. I will sit here and show you how to write some simple things from scratch and explain how does it work. Because in this field, the practice is very important. So all these theoretical concepts are not too important if you're not able to do it on computer. Okay, now it's time to discuss the general outline of our course. So today is our first lecture, Introduction to Euler Equations. So the most important thing I would like you to keep in mind after this lecture is this system of equations. How did we get it, and what does it mean? And as well as some general concepts that we discussed. So Mach number, shock wave, supersonic flow, that what is computational gas dynamics, why do we need that, so all these things. Next lecture will be next Friday because of holidays, right? So next Friday. Hopf equation is a simplified analog of Euler equations. So as I told, the Euler equations, they are difficult. And it would be great to discuss the concepts, the types of solutions on the example of just one scalar conservation law. So we start with not the system of three nonlinear equations. We will start with just one equation. For sure, one equation, although it contains the main types of flows, types of solutions, it's not able to provide the same structures, wave structures, just Euler equations. But nevertheless, it's very important to know the concepts of shock wave, Riemann problem solution, expansion waves, and many other very useful things from scalar conservation law, Hopf equation. Then two lectures. Okay, so during these first two lectures, we should understand the object. So we need to know how to solve Euler equations. Okay. After that, we will move to numerical methods. So we should solve Euler equations using one and another numerical methods, and the question we should know the basic concepts. They are convergence, consistency, and stability. I will explain to you on the example of just one ordinary differential equation. And I think that one lecture I will explain you all the concepts, and another lecture we just write for one example. We implement a number of numerical methods, and I will show you what does it mean, different orders of accuracy, what does it mean stable scheme, unstable scheme, what does it mean in reality that the scheme is unstable, how can we see it, and so on. Although all these concepts, convergence, consistency, and stability, for partial differential equations, they are in many senses similar to those for just ordinary differential equation. They're not the same. And so the next lecture will be about basics of finite difference schemes, but for partial differential equations. And it will be on the example of linear direction equation. So linear direction equation, we will discuss it next time, is the simplest possible linear analog for Euler equation. Just one hyperbolic equation. And very important, and it's possible to explain the most important things on the example of linear direction equation. And the next lecture will be about numerical schemes. So we'll discuss the basic schemes such as Coulomb-Jackson-Riess numerical scheme, Lux scheme, Lux-Vendroff scheme, Godunov scheme. So what are relationships between all these numerical schemes? And once again, one lecture I plan to have some practice lecture when once again I will show you what does it mean and how can we implement all these numerical schemes, and show you the main properties in practice. Then finite volume methods for 1D Euler equations. So everything here from the second to the seventh lecture will be about just analog equations. So toy model, simplified model. So they will be not about Euler equation. They will be about simplified models. But during this lecture, we should know the basic concepts. After that, finite volume method for Euler equations. So here for 1D Euler equation, I will explain what does it mean finite volume method, give you some historical perspective, some history of this question. That's very interesting and very important. So what does it mean, finite volume method? So pros and cons, and so why is it so important? Why is it so widespread, and so on. The second part, the last 8 lectures, we will discuss the properties of Euler equations. So as I told you, my goal is to show you how to build numerical methods, take into account the properties of the Euler equations. We start with discontinuous solution of the Euler equation, shock waves and contact surfaces. Actually, we will get the expressions. We will get the expressions that can be, and using these expressions, it's possible to get this analytical solution, but for the oblique shock. We will discuss the normal shock. So we will discuss these different types of solutions of Euler equations without relationship to numerical methods. So just theoretical consideration. So the Euler equations, they admit discontinuous solution, and we'll get it. Refraction waves have self-similar solution of the Euler equation. So another class of solution is refraction wave. And after getting all the necessary expressions for shock waves or contact discontinuities for refraction waves, we will have everything in hand to build the solution of Riemann problem. And the Riemann problem solution is also actually, on one hand, it's just fundamental issue from Euler equations. But on the other hand, as it was shown by Godunov and Lux and many others, there is a strong relationship between the solution of Riemann problem and numerical schemes for Euler equations. And in this sense, I will show you how the knowledge of the solution of the system of equation can be used for the construction of the numerical scheme. But again, so this will be just theoretical consideration, Riemann problem for Euler equations. And here, next lecture, will be about construction of the numerical method that will use the solution of the Riemann problem for Euler equations. The method that for the solution of Euler equations that use the solution of Riemann problem is called Godunov method, or method based on exact solution. The problem here that closer to equation that numerical methods can be more, economical or not. Computational cost actually is an important issue. That is why the next lecture will be about approximate Riemann solvers. So what should we do if we need accurate solution, but we do not want to have huge computational costs? But once again, it's again about tradition. For example, I educated in Russia, and my supervisors were some from Soviet scientists, and at that time, they did not. So the most important issue was to get the correct solution. They did not pay much attention to the computational costs. That is why, again, traditionally, for example, I enjoy Godunov method, although it's very computational. So, but in Western universities and in United States and Canada and Europe, people usually do not use Godunov method because it's too expensive. They use HLL or HLC or OSM method or something like that. But from some traditions and historical point of view, actually in Russia still, so the Godunov method is very, very popular. So it's very difficult to say to have some general common answer for which method is better and so on. So after that, finite volume method for 3D Euler equations. So actually here we will finish the consideration of numerical methods for 1D equations, some basics, and I will show here for sure you some numerical examples, maybe some lecture will be with practical part. Then 3D. So I think it's important to show you how, not some general theoretical concepts, but I'd like to show you real practical procedures. So how to write, how to create real working algorithm for 3D simulation of arbitrary computational grids. Finite volume method for 3D Euler equations. And last two lectures, I believe, we can discuss the problem of the construction of high order methods. So everything from the beginning to here, although we will discuss some high order methods here, we will discuss when we will deal with schemes for linear direction equation. But the last two lectures will be about the most actually current issue in this field. So the problem here that all this is first order methods, so they are low order methods. So they are not so practical because nowadays people try to use high order methods. But it is known from theory that if you use high order methods, they cannot be monotonic in linear sense. It means that if you want to use high order methods, you will get the unphysical oscillations, pulsations, and you need to add some approaches, some methods to avoid these unphysical oscillations. And actually, on this way, there are a lot of results, and we will discuss actually two main approaches: so Maskell type scheme and more common concept of total variation diminishing methods. How to build how to build the high-order numerical methods for hyperbolic equations, for Euler equations that can be used in practice. I mean, without spurious oscillations. And that's it. So this is the expected outline of our course. About books, recommended books. So there are the most well-known books in this field. So thorough, Riemann solvers and numerical methods, a practical introduction. So the title is correct, it's practical introduction. So it's a really useful book. It contains a sample of codes, and actually I use them even in my scientific research. And so that's a great book, and I recommend you to read it and to have it. It's not too theoretical, so indeed it's about practice. The third one, finite volume methods for hyperbolic problems, is much more theoretical. So if you need to know some theories of these results about nonlinear concepts of stability, so these TVD criteria and so on, about the entropy conditions, so this is much more theoretical book, but I also enjoy it. And then if you want to be an expert in this field, you should read it. I enjoy this book very much, Computational Gas Dynamics, because it provides very difficult concepts in very simple words. So it's very concise and provides all the concepts in very simple words. And again, this book of Anderson, I have already told to you, this book is very popular in China, and it's more about aerodynamics, yes, but also it has some chapters about numerical methods, and they're also written so they should be useful for practice, right? Not just from some theories. So I think that all these books is enough for you. Actually, because once again, our course is in English, I do not provide you books in Chinese. Actually, there are also books in Chinese similar to that. If you have any difficulties, we can discuss it. But actually, I recommend you this. They're all available on the internet, but I can also send them to our chat when we will create it. Right? Yes. And that's it. Actually, the last slide that I usually show here. What is our course about? So our course is about this picture. So, but this picture was that was drawn several years ago. So, yeah, the problem is that CFD students now try to, many of them, just to skip all mathematics, fluid mechanics, fundamentals of CFD, and just to use CFD software. That's not so good. Yes, so there are cases when it's appropriate, maybe for some engineering application, I don't know, but actually that's not good. Actually, we're about fundamentals of CFD. Our course is about here. Maybe something fluid mechanics plus fundamentals of CFD. I believe that you know the mathematics and you know the big part of fluid mechanics, and then we can move forward. But last year, so the picture was updated. Now it's AI for CFD. So maybe CFD software is not so bad, and but this one is even worse. Also, there are many pictures. So actually, the serious CFD community, they do not like AI because they do not see much result from that. So it's believed that it can indeed provide some meaningful results in some turbulence models, adjusting parameters for that. But it looks like nowadays there is no alternative in just classical CFD simulations. You are not able to substitute weeks of convergence in some problem just by a wrong answer from AI within several seconds. So my goal is that we will be here and know some knowledge here, and after that maybe we can go further. Okay, that's it. Thank you so much, and we can discuss if you have any questions now.